It's challenging to build VR apps. And why wouldn't it be? VR is a fundamentally different platform than any of its predecessors. The performance requirements of VR can be extremely demanding, as our Quest 2 apps have to render 2 separate eyes at least 72 frames per second, often higher, and at extremely high resolutions, all of which can create a daunting environment for you developers to handle. So it's no surprise that our developers view optimizing performance as the single most important variable when it comes to shipping to a platform like Quest. Some of our developers have had to make excruciating trade-offs, having to eventually cut content and features that they would have liked to have had in their apps, but which just could not fit in the Quest hardware budget. And that is why we are thrilled to announce that we've built a feature which achieves a step function improvement in both performance and latency at a magnitude that even we ourselves would have previously thought unattainable. And it's called Application Spacewarp. In our initial testing, Application Spacewarp gave applications up to 70% additional compute, potentially with little to no additional artifacts. It works by allowing the application to render at half frame rate from its original refresh rate, which will provide the app with up to 70% more CPU and GPU compute budget when rendering a given frame. You might be curious how we came up with that 70% number. Testing Application Spacewarp in 2 titles showed that those applications had up to 70% additional CPU and GPU compute. And we found that these applications have very similar workloads to most apps on our Quest store. So we think a large portion of all of our Quest apps will also benefit from a very similar 70% improvement. Application Spacewarp is one of the most substantial optimizations that we have ever shipped to Quest developers. And it can significantly reduce the pain you may have experienced to bring your app under budget, while allowing you to concurrently ramp up the visual fidelity of your games and apps. We do want to point out, however, that there are some scenarios where Application Spacewarp may not be the perfect fit for your content, as it may introduce too many artifacts or might require a significant rework of your application. We'll address all of this later in the talk, and you can read more details in our documentation online. So when hearing about this incredible performance win that Spacewarp provides, your immediate reaction might be that this sounds a bit too good to be true, right? Especially because this improvement is not even based on any new hardware. Yet the sheer magnitude of that improvement is almost exactly what you would expect from a generation of hardware advancements. So, how do we do it? Well, allow us to spend this session diving into the ins and outs of this new technology, covering everything from how it works, what you'll need to do to enable it and benefit from these performance savings in your apps, and most importantly, an unbiased view of the pros and the cons of this technology. Buckle up and let's get started. As an introduction, I'm Neil Bedecker, and I'm extremely excited to be joined by my colleague, Jian Zhang, the lead architect for Application Spacewarp. Jian, take it away.
Thanks, Neil. Application Spacewarp is based on a simple idea of allowing application to render at half rate. For example, 36 compared to 72 FPS, while also having the application render a motion vector buffer and a depth buffer, which our system will then use to generate new frames and still output 72 FPS to the display. The following diagram illustrates the difference, focusing specifically on the GPU execution occurring on device. Here is what a normal 72 FPS application looks like. 1000 milliseconds divided by 72 is 13.9 milliseconds. So that's the per frame total budget, which has to be split between the application and our compositor. Every frame, our compositor in the backend is performing composition work to push the rendered images onto screen. Since the application and the compositor are sharing the same GPU, for example, if the compositor is taking away 1.3 millisecond per vsync, then the application has 12.6 milliseconds to use every frame. Now, the second diagram shows what it looks like when an application is running 36 FPS with Spacewarp. 1000 milliseconds divided by 36 is 27.8 milliseconds, which is the total time per frame again. Now, with Spacewarp on, the compositor will be slightly more expensive. For example, roughly 1.8 milliseconds per vsync. Now the app will also need to spend some time on motion vector generation too. For example, 2.5 milliseconds. After taking away all the extra overhead, we have 21.7 left for application to use per frame. So, as you can see, the GPU time that the app can use is increased from 12.6 milliseconds to 21.7 milliseconds per frame, which is 71% more budget. To be noted, for each application, the actual numbers might be varying, depending on your app's actual content. Now you may be familiar with PCSW, which was previously released for Oculus Rift apps. Even though there are a few similarities, we want to call out that the PCSW is a very different technology than application Spacewarp, which we are introducing today. PCSW is a technology for Oculus Rift and Link apps, whereas application Spacewarp is for native Quest apps. Application Spacewarp is a completely developer-driven feature. The developer has full control on motion vector generation and can decide when the feature is on or off. Now that we have given a high-level overview of how powerful application Spacewarp can be, it's time to go a bit deeper on the technology's detail. Until now, we have mostly described Spacewarp as a system which generates new frame out of thin air. As much as we'd love if this was true, the magic comes from the quality of the motion vector themselves, which are rendered by the app. On a given frame n, the application is now responsible for rendering to a lower resolution depth buffer and a motion vector texture, which represents the movement of its pixels from one frame to the next. Since there are many different methods and conventions to generate motion vectors, let's take a closer look at exactly how applications should populate this motion vector texture. Our motion vectors are generated using a simple idea of a graphics pipeline. If you are familiar with standard graphics features like motion blur or temporal anti-aliasing, those techniques generate motion vectors using a very similar method to what we use. One day in the future, we might even use the app-rendered motion vector for other graphics features, so that the overhead of generating the motion vectors can be shared among different features. Let's consider how motion vectors will be generated for the simple scene shown here, which is simply one cube moving sideways. The so-called motion vector is just a projected screen position difference between previous frame and the current frame for corresponding pixels. We often say a picture is worth 1,000 words. To an engineer, maybe we can replace this by saying that one line of code is worth 1,000 pictures. The most important point about the motion vector generation here is that it transforms each vertex in every object to clip space, not only for current frame, but also for previous frame. Then in the fragment shader, we convert them into NDC space, which are the clip space positions normalized by the W component. Once you have the NDC space positions in the fragment shader, one for current frame and one for previous, you simply take the difference of them, and that's it. That's your motion vector for the given pixel. You might have noticed in the code, the motion vector is a 3D vector instead of a 2D one. That's because we take the depth motion into considerations as well. which can further improve frame extrapolation accuracy. And finally, here is what the motion vector looks like in action. As you can see, in addition to the full resolution color eye buffer, we also render a lower resolution motion vector buffer which represents 3D motion of the pixels. Furthermore, we also collect the depth buffer in the motion vector path. Since the motion vector render path will always have a depth buffer, there is not much you need to do. Just resolve it into system memory and share it with our runtime. The depth buffer is a very crucial part of the pipeline, since our runtime uses it to do positional time warp for latency optimization, which we will talk about later. Another key point here is about performance. Since the motion vector buffer's resolution is much lower than the eye buffer, and the motion vector shader is usually much simpler than the main path shader, the motion vector path is usually much faster than the main path, both on GPU and CPU. This is great because it means the performance cost of the motion vector path is usually small. So, to wrap up our initial motion vector discussion, in a standard 72 fps setting, the application renders to its eye textures. Our composition software takes the submitted texture and outputs a composited result to the screen, also at 72 fps. In a 36 fps Spacewarp setting, the application is responsible for rendering not only its eye texture, but also now populating this motion vector texture and depth. But the key here is that our composition software is still rendering at 72 fps, so our screen refresh rate does not change. It stays at 72, but the application itself only needs to perform rendering at 36 fps. That's how we can maintain such a high quality bar with often very few or no perceptible artifact when enabling application Spacewarp. And of course, the app enjoys a huge compute budget increase per frame along the way. We have covered a lot of topics so far, showing how application Spacewarp can give your Quest app an incredible amount of actual compute, as long as your app renders a motion vector texture which defines the motion of your app's eye texture from last frame to the current frame. Now it's time to switch gears a bit and discuss the obvious elephant in the room when rendering at half frame rate, which is latency, as well as how we have moved that needle forward. Let me hand it over to my colleague Neil to talk about this in more detail.
Thanks for the great description of the core tech behind application Spacewarp, Jen. I'm excited to share 3 key latency improvements that we've made to support this feature. Now, viewers who are paying very close attention may recognize the obvious challenge that exists when the app renders at half frame rate. And that is that the app's input latency will nearly double. At a very high level, this can be imagined by realizing that most of the input latency of an app comes from sampling input once per frame at the very start of each new frame. If we only render at half rate, we are only sampling half as often, and so the latency will be twice as high. But rather than accept this fate of a twice as high latency figure, we've identified all possible sources of latency savings in our entire end-to-end graphics pipeline. And we implemented 3 extremely important and complementary techniques: phase sync, late latching, and positional time warp, also known as PTW. And we're excited to share that phase sync and late latching can reduce input latency and rendered latency to much lower levels that we feel are perceptually equivalent to the latency of a full frame rate app that doesn't even use these latency optimizations. We found a way to shave off nearly half of the entire rendered latency for our Spacewarp apps that are running at half rate. And then there's PTW. When enabling PTW in your Spacewarp half rate apps, head pose latency will be even lower than the latency in equivalent full frame rate apps that do not use Spacewarp. Isn't that shocking? What we're saying is that your Spacewarp apps, which use PTW, will have a lower head latency than the head latency of any Quest app which is currently on our store, since none of them are using Spacewarp or PTW. That's quite a statement we just made. We're using late latching and phase sync to dramatically reduce the input and rendered latency of Spacewarp apps. And then with PTW, we have a total head latency figure which is below that of any full frame rate app that does not currently use Spacewarp. Well, allow us to spend the next few minutes to describe exactly how we did it. When we refer to the word latency here, we're referring to the difference in time between when a head or controller pose is sampled by the app and when that final frame is displayed. That's a very standard definition of latency in VR. But latency can also have many different definitions in many different contexts. So we just wanted to clarify exactly what we mean here. Here are two images visualizing the type of input latency that VR apps face. The first image is for a standard 72 FPS app. For the sake of an example, we'll assume that this given app has a main thread, a render thread, and then begins to perform GPU executions for the given frame once its render thread is complete, which is a very standard pipeline approach that most apps in our platform currently use. Let's look at points A and B on the first diagram. Typically, these are the only spots in the frame loop where the app will update its poses, which means it fetches a new pose from our XR runtime. A is the very obvious natural point. It's right at the start of the frame, since the head and controller poses will then be used for any simulation logic done right there in the main thread. And then B is a slightly lower latency point at which the head and controller poses will get a bit updated, so that they'll be rendered at a lower latency a little later in that frame loop. Pretty straightforward stuff so far. This is the system that was in place before any of the recent optimizations that we are talking about today. We can see how the pose sampled at A has a total input latency which is equal to the difference between A and the display time. But now, let's compare that to the disastrous case of enabling 36 FPS in application Spacewarp, but without any of the latency optimizations that we're describing now. This can be seen in diagram 2. As we can see here, we also have that standard A and B for the start of each thread, but now the display time of this given frame is way further into the future. This is actually expected, as we're now rendering half as often, so the delta between the start and end of the frame will be significantly longer. We can assure you that if we just accepted having higher latency and just gave up right there, then our users, and more importantly, the users of your apps, would notice, and it would be a very subpar experience. Thankfully, rather than resign ourselves to the non-ideal fate of accepting high latency with application Spacewarp, we will use phase sync and late latching to come to the rescue. They will reduce this combined latency figure by enough to make the end-to-end latency, specifically rendering latency, acceptable. Let's start by going through the gist of phase sync. We won't go into every underlying detail about how this technology works, but the key details to understand are that the application performs rendering work on the GPU, but only after this work is complete can our composition software jump in, take that application rendered frame, and composite all together. Conceptually, phase sync is simply a technique to minimize this delta, which is that delta time between when the application finishes rendering work for a given frame and when our composition software begins its composition rendering work for that same frame. In practice, phase sync works by shifting the entire execution of your application rendering pipeline just a little bit later, depending on a dynamic heuristic that seeks to minimize this delta, since a lower delta means a lower latency. Just how much latency savings can you expect from FaceSync? It all depends on your content complexity. If your app is running very quickly, FaceSync will help you the most and provide several milliseconds of latency savings. Most importantly, both input and rendered latency. However, if your app is pretty much maxing out every last bit of GPU and CPU compute already, you actually won't get too much of a saving from FaceSync. Instead of seeing this as bad news, there's actually a silver lining, which is that when we said FaceSync was complementary to late latching, we meant it. Because the case where you don't get much FaceSync savings is the exact case where you get the maximum late latching savings. So now let's shift gears to late latching. To decompose that effect of what late latching does down to one single concept, let's look at what the render thread executions look like for a given frame. This image here represents the render thread of a standard app rendering at 72 FPS. As we said earlier, the latest spot in the frame loop that the head and controller poses will traditionally be fetched is at point B. Right after point B, we begin all of our rendering work. This consists of standard render thread executions, like setting up our uniform buffer values specifically, which happens to be the area where our head and controller poses will be finalized, since the head pose eventually makes its way to the view matrix and the controller pose affects the object to world matrices of individual rendered objects. That happens after point B, the spot where we upload these view and object matrices to uniform buffers. So it would be really fair to assume that B is the absolute last spot that we can update these matrices. After all, we push them directly to uniform buffers right after that. So we can't do any better from a latency standpoint there. Right? Wrong. Late latching is ultimately built on the concept that when using the Vulkan Graphics API, we can actually update our uniform buffer memory region even after that initial write to the region. Why? Because it's perfectly safe to update this memory region until we call VKQ submit, which then submits a series of commands that have been queued up and essentially puts the GPU in motion. And until the GPU begins executing, we can actually continue to write to the addresses that hold these buffers. Now, VKQ submit is executed at point C on this diagram. So, in essence, the latency savings of late latching come from the fact that the render thread is performing a lot of vital work. Yet for most of the duration of it, the GPU has not even begun execution yet. So we still have an opportunity to update our Oculus pose-dependent uniform buffers right before the GPU actually begins work for this given frame. And just how much latency can we save with late latching? Well, considering that previously, the last point at which we updated poses was point B, and here we know that we can safely update poses until point C, the late latching algorithm will be able to save nearly the length of C minus B milliseconds. Since C minus B represents the length of the render thread, this could be as high as 25 milliseconds on an application Spacewarp app, and even up to 13 milliseconds on a regular 72 FPS app. So, you do not only want to be enabling late latching in your application Spacewarp apps. You should actually have it on all the time. And finally, as for how to enable late latching in your Unity and Unreal Engine apps, check out our blog post online, which has instructions as well as a link to the documentation with more details. And if you happen to be a native developer, you are welcome to implement late latching on your own, since the feature is fundamentally an app side change. So you will have to make it work with your own app, ideally following a very similar mold to the one that we just laid out here. So, we've talked about how late latching and FaceSync can drastically reduce the render latency of your app. But we can actually do even better. And it's all because of that one detail that Jen shared earlier about how application Spacewarp requires submission of a depth buffer, along with the motion vector, to our runtime. The use of this depth buffer allows our composition software to perform positional time warp, known as PTW. So, what exactly is positional time warp? A lot of people are familiar with time warp, which is a reprojection technology that corrects HMD rotation at nearly the very end of the entire graphics pipeline, specifically the last few milliseconds right before we composite that frame to the display. Time warp works great and has no doubt been one of the most impactful features in our entire tech stack since its creation years ago. However, time warp only corrects HMD rotation, not HMD translation. Try and imagine a case where the user is translating their head left and right very quickly. Since time warp only corrects for rotational differences, the translational differences in head motion through a given frame's execution will lead to an artifact that cannot be corrected by traditional time warp, especially in near-field objects. Enter positional time warp. When application Spacewarp is enabled, our composition software can read depth values from the application submitted depth buffer, which gives us the opportunity to do HMD translational correction in addition to the standard time warp rotational correction by performing depth reprojection. Remember the point we said earlier about how our composition is still running at full frame rate, even though the app is at half frame rate? The beauty of PTW is that it's of course happening inside the compositor. So every single frame which is composited to the display will benefit from this positional latency correction. And this is why, from an HMD translational latency point of view, we can quite literally say that when using application Spacewarp, head motion latency will be lower than the latency on full FPS apps which are not using Spacewarp. And since every app before today is obviously not using Spacewarp, then using PTW with Spacewarp will give your apps lower head motion latency than they have ever had before. So, that was all definitely quite a lot to take in. We presented 3 separate latency techniques, each of which focus in a different portion of the end-to-end graphics pipeline, and each of which complement each other to all add a significantly lower input and rendered latency to your Spacewarp apps, while also giving those apps a lower raw latency figure than any non-Spacewarp app can attain. And for these 3 features, Phase Sync is the easiest to enable, since it will be enabled by default in all OpenXR Oculus apps. Then PTW is also pretty easy to enable, since as long as you submit the proper depth buffer, PTW will work out of the box. And for late latching, finally, you should check our documentation online to understand the necessary steps to enable it in your apps. Now, it's time to switch gears a bit. So far, we've presented application Spacewarp as an incredibly powerful feature that can give you an increase in compute power that's almost too high to believe. But with that great power comes great responsibility. And to understand how to wield the power of Spacewarp responsibly, you must understand the scenarios that Spacewarp performs well in, as well as some other scenarios that it performs a little less optimally in. We want to make it abundantly clear the fact that this feature is not a silver bullet and may not be suitable for every single app in our platform. So now that we've presented both the foundational technology of application Spacewarp, as well as supporting latency tech that allows this feature to be at a very high quality bar, Jen is going to discuss some specific content requirements and best practices that are pretty much required if you want your app to render high quality Spacewarp frames.
Thanks, Neil. So like Neil said, application Spacewarp is a very powerful tool for developers, but also not a silver bullet to just boost your computing budget without any effort. Ultimately, it's your responsibility as a developer to decide how and when to use this tool. Let's begin by talking about the case of transparency. It's easy to say that transparency rendering will be challenging under Spacewarp. The reason is that for each pixel, we can only have one single value for the motion vector and for depth. Basically, the whole principle of transparency is to let two different pixels at different depths be combined and have their color blended together. Imagine a case where you have a transparent object moving left on top of an opaque object moving right. For a pixel that contains both objects, the motion vector will be ambiguous, since the pixels are moving in both directions. Luckily, the problem isn't as bad as it might seem for a lot of cases. For example, if the transparency surface is far away from the camera, this case is probably fine, since the actual projected motion is usually very small from frame to frame. Also, for particle effects, which is a big use case of transparency rendering, a little bit of motion jitter is usually less noticeable, since the effect often comes with fast animation itself, for example, with explosions. The important case that we want to avoid is for near-field, fast-moving objects to be transparent. A great example is the controllers, which are usually very close to the HMD and also moving fast. So if possible, you might need to design the controllers and any children objects of the controllers to be application Spacewarp friendly. We don't think this is a very hard trade-off to make though. Giving up transparency near-field objects for a feature which gives you so much more computation budget is a pretty fair trade-off in our opinion. And checking our store apps, many apps don't use transparency surface anyway, so we hope this is not a big restriction. Next, let's talk about background distortion. Spacewarp is a frame extrapolation tag, so it's moving pixels around. We have tweaked the process to reduce potential artifacts, but it might still introduce some image distortion, especially on the background. Normally, if the background has rich texture patterns, just like what most video games are rendering, you probably never notice that. For example, the image on the left. However, for some particular situations, like the right image here, human eyes are very sensitive to catch the subtle distortion on the super simple and clean background. If you notice that is a problem in your apps, you might need to do a bit of content tweaking to make sure that the background is more Spacewarp friendly. This is definitely a subjective metric. It's something you will have to test until the quality bar is acceptable for your app. Finally, let's talk about fun one, which is what happens when the rotation speed of your objects are too high. Let's imagine you have an animation in your scene, which is a cube rotating around at an extremely fast rate, maybe 100 rounds per second. In this case, the cube's orientation from a given frame to the next will seem more or less random, since the cube moves so fast that the motion vector cannot accurately be constructed. The motion vector might even point in the opposite direction. So in this example, you could work around this issue by tuning down the box rotation speed, so the motion vector would be more reasonable. Or, there is also another way to handle the problem, which we currently use in our UE4 integration. We can detect a very high rotation in the motion vector shader, and then disable the portion of motion vector coming from the object motion. If you do this, you will still have PTW working, but the object motion vector will be ignored. And in practice, we have seen this actually works pretty well. Most of all, if your object is rotating like crazy, you most likely cannot notice object jitter either, since your brain expects a lot of object jitter already. This is an important case which highlights that ultimately motion vectors are very powerful, but will only work if your content can generate useful motion vectors. The takeaway you should get from this section is, just give your motion vectors a chance to be useful. You might also find different corner cases than what we listed here. And you can either avoid them by changing the content, or investigate a bit to find your own ways to work around it. Sometimes, we just need to be creative. For example, we listed the transparency issue as the #1 challenge. But is this really unsolvable for your case? Probably not. If your transparency surface alpha value is quite high, you can choose to convert it into an alpha-tested opaque material and render it into the motion vector path, while keeping your main path shader unchanged. And if the alpha value is very low, the motion jitter might not even be noticeable at all. And also, in our integration sample, we recommend to render the motion vector texture in a dedicated path. But is this the only solution? Probably not. How about using MRT? How about reconstructing the static background motion vector from depth? There are so many different ways to achieve the same goal. Please remember, you, the developer, are the owner of the motion vector. You can change it however you like. At last, you will have the ultimate control on when to enable this feature and when to disable it in any frame. Please check our developer docs and blog posts for more discussions on this. And we are looking forward to hearing your special cases and your creative solutions. Next, Neil will show you how to enable the tag in your apps.
Thanks, Jen. We're extremely happy to announce that we have a full game engine integration with application Spacewarp, both on Unity and Unreal Engine. These are all built on top of our OpenXR extension APIs as well. And of course, all of you native developers out there can directly use that OpenXR extension called XRFB Spacewarp to enable that feature in your own apps. And please check out our developer documentation and blog posts for more detailed information. Spacewarp is a hugely powerful, but also complex feature that will require close attention by you. And hopefully, we will have clarified any of your questions in our documentation online as well. So, we've really covered a lot in this jam-packed session today. Jen gave you an overview of both the underlying technology of application Spacewarp, as well as a lot of app-specific considerations that you're going to need to keep in mind to ensure that Spacewarp meshes well with your own content. And then I presented an in-depth look into some of the immense latency savings that you can see in your Spacewarp apps, and we hope all of you developers will enable phase sync, late latching, and PTW to achieve the lowest latency experience. Finally, as you can see, using application Spacewarp is ultimately a collaborative experience between you, the developer, and us. And even though it may seem like the feature development of Spacewarp is complete on our end, the honest truth is, we see the Spacewarp journey as just beginning. Ultimately, we hope to see Spacewarp in as many of your apps as possible, taking what you've learned today and by reading the online documentation to make your app successful. Feel free to reach out to us in any way. Feedback, comments, and especially bug reports are always much appreciated, as they are the only thing that will allow Spacewarp to be truly hardened. Thank you so much for your time. It's been a real pleasure.